Thank you. My name is Alia, and I'm here on behalf of Slovenian team, who will be talking about how to fight sepsis. Our team was composed of 8 students, all undergraduates of microbiology, biochemistry, and physics. And we spent the summer working on the National Institute of Chemistry and in the laboratories of the University of Ljubljana. And what did we work on? We were really interested in eukaryotic cells, more precisely mammalian cells. We realized that even though they can be compared to prokaryotic systems, they are far more complex and much more time and money consuming to work with. But still, the challenge of understanding a system that complex was too great. And with the potential medical application that our work had, our goal for the summer was set. Talking about medical application, there's one specific problem that soon caught our attention, and that is sepsis. Sepsis strikes over 750,000 people per year in the US alone, and in 1 with 5 cases, it ends with the death of the patient. It claims the lives of more people than breast and lung cancer combined, and that is why it is ranked among the top 10 causes of death in the US. But still, many people don't really know what sepsis is. Sepsis, that is systemic inflammatory response syndrome, is a pathogen-triggered excessive inflammatory response that is a widespread activation of inflammation and coagulation pathways. In sepsis, the excessive reaction to the pathogen, rather than the pathogen alone, is what causes pathology. TLR, that is toll-like receptors, are the main gatekeepers of innate immunity, that is the fast-acting, not antibody-mediated branch of the immune system. It was long thought that innate immunity is relatively non-specific, but the discovery of TLR receptors showed that with their help, the innate immunity can recognize several different molecules that are distinctive for pathogens. So far, 11 different TLR receptors were recognized in mammals, and they can recognize and bind several different pathogen-associated molecules, such as the double-stranded RNA, flagellin, or lipopolysaccharide. I will now show a simplified diagram of how TLR signaling works. After the binding, the recognition and binding of so-called PAMPs, that is pathogen-associated molecular patterns, to the TLR receptors oligomerize and are therefore able to recruit a MyD88 molecule from the cytoplasm. MyD88 binds to the cytoplasmic domain of the TLR receptor, and subsequently other molecules join the complex, such as IRAC1, 4, or TRAF6. A series of activations by the means of phosphorylation takes place, and it includes several different cytoplasmic proteins. At the end, an IKK complex gets activated. IKK is a kinase that is able to phosphorylize an inhibitor of the nuclear factor NF-kappa B. NF-kappa B is a really important transcription factor, and after its inhibitor gets phosphorylated, the NF-kappa B is released from its inhibitory complex and is able to translocate to the nucleus, where it causes the transcription of several different inflammatory molecules. Well, this hymn is only a very simplified version. The real TLR signaling pathways are far more complex. But still, if you look at this diagram more carefully, there is one molecule that stands out. That is the MyD88. MyD88 is involved in the majority of all signaling pathways, and MyD88 is where we focused our attention. The basic concept and the goal of our project was to inhibit excessive cellular activation, but without completely inactivating cellular responsiveness. Our genetically programmed cells would therefore be able to respond to inflammation, fight the infection, but without the danger of developing sepsis. We implemented that by inserting into mammalian cells sort of a feedback device with an inhibitor that is a dominant negative MyD88. Dominant negative MyD88 is a form of the wild type MyD88, which is able to bind to the TLR receptors, and by binding to the TLR receptors, it prevents the wild type MyD8 to bind. Therefore, signaling pathway is blocked. We planned to repress the signaling pathway only for a limited period of time. After the binding of dominant negative MyD88 to the TLR receptor, like I said, the signaling pathway is blocked, but only until the dominant negative MyD88 is degraded. We planned to speed up the rate of degradation by adding a PEST tag to the dominant negative MyD88. A PEST sequence would enable faster degradation of MyD88 so that normal cellular responsiveness would be regained quickly. After the removal of an inhibitor, wild-type MyD88 would be able to once again bind to the activated TLR receptor, and normal cellular responsiveness would be regained if the pathogen would still be in the vicinity. We engineered a mathematical model, and here you can see that after the binding of the pathogen-associated molecular patterns to the TLR receptor is able to recruit the wild-type MyD88 from the cytoplasm, and a signaling cascade is triggered. At the end, the signaling cascade leads to the translocation of nuclear factor NF-kappa B to the nucleus, where it triggers the transcription of different inflammatory mediators. In our genetically modified cells, in which we implemented a feedback device, the nuclear factor NF-kappa B would not only trigger the transcription of RNA for inflammatory mediators, but also the transcription of our dominant negative MyD88. MyD88, the dominant negative MyD88, would then be able to act as a competitive inhibitor. It would compete with the wild-type MyD8 for the binding to the activated TLR receptor. A DN-MyD88 combined to an activated TLR receptor, but it cannot trigger the signaling cascade. So a state of tolerance is induced in our cells. Based on this mathematical model, we ran several simulations. Here you can see in wild-type cells, after of initial stimulus of an appropriate TLR agonist, the cytoplasmic amount of NF-kappa B drops because it is translocated to the nucleus. And in the nucleus, NF-kappa B triggers the transcription of several different inflammatory mediators. In wild-type cells, a second stimulus of an agonist would trigger the transcription of an equal degree of inflammatory mediators. But on the other hand, in our cells, which we would transfect with a feedback device, a second stimulus of an agonist would only cause a slight degree of renewed activation of inflammatory mediators. Because during this first stimulus of an agonist, not only inflammatory mediators would be transcribed, but also our dominant negative MyD88, which would then, during the second stimulation, bind to the TLR receptors and partially block the signaling pathway. In order to test this hypothesis in practice, we started constructing our BrioBricks, and this proved to be quite a demanding task. None of the previous iGEM competitors ever worked with mammalian systems, so we had to start building our BrioBricks from scratch. Still, we managed to build quite an extensive list of BrioBricks, and these are the ones that we actually registered. We decided to register only those that proved to be mutation-free after having sequenced them all. All of these BrioBricks are already available to all the future competitors who will be interested in working on mammalian systems. We built appropriate fusion proteins using the PCR overlap extension method, and we cloned them into the C to the B domain in BrioBrick plasmids. We decided to modify one of the BrioBrick plasmids by permanently inserting a eukaryotic terminator directly following the cloning site. A terminator which we inserted in the BrioBrick plasmid enables efficient stop of transcription in higher eukaryotes. And this vector is already available to all the future competitors. The final composites were constructed using the standard BrioBrick assembly technique and were transfected into human embryonic kidney cells. We used a cell line that doesn't express TLR receptors on its own. Therefore, we were able to transfect those cells with the TLR receptor of our choice. Of course, BrioBrick building was only a minor part of our project. The majority of summer was spent doing experiments using a variety of different detection systems to monitor the time course of the cellular response. ELISA was used for the detection of the amount of free NF-kappa B. The amount of free NF-kappa B is correlated to the state of cellular activation, because when cells get activated, NF-kappa B is released from the inhibitory complex. It is therefore able to bind to the NF-kappa B binding site, which we used on our probes, and with the help of primary and secondary labeled antibodies, we measured the level of free NF-kappa B. We showed that with increasing time of stimulation, there is also an evident degree of higher NF-kappa B levels in the cytoplasm. With flow cytometry, we detected the level of phosphorylated ERK kinases. ERK kinases are one of the kinases that are involved in the TLR signaling pathway. And we showed that the stimulation causes an evident rise in the level of phosphorylated ERK kinases. Still, both the ELISA and the flow cytometry method would need further optimization to gain better results. That's why, with the majority of our experiments, we used the luciferase assay. The dual luciferase assay uses two different luciferase reporter enzymes, which are both transfected into cells at the same time. The F-luciferase, the firefly luciferase, under the inducible NF-kappa B promoter, is used to detect the transcriptional activation of our system. The R-luciferase, or the Renilla luciferase, under the constitutive CMV promoter, is used as a control. It enables us to overcome the problem of uneven transcription, of uneven transfection. So, one of the experiments was conducted because we wanted to test how the paste tags that we used on our constructs work. We used the paste tags to increase the rate of degradation of our inhibitor MyD88, and we showed that the luciferase, which have the paste tag, are degraded much more rapidly than the luciferase without the paste tag. We also tried to detect the expression level of proteins under the NF-kappa B promoter control. NF-kappa B is an inducible promoter which we used on our constructs, and we've shown that with increasing time of stimulation, there is also an increase in the expression of proteins under the NF-kappa B promoter control. But still, why is there no inhibition? We expected inhibition to occur because after stimulation of cells, the dominant negative MyD88 should be transcribed and bind to the TLR receptors and stop the signaling pathway. Perhaps here is where the answer lays. All of our fusions were done on the C-terminal of MyD88. The C-terminal represents the tier domain of MyD88, which interacts quite closely to the cell membrane. Now, this is the C-terminal. and the TLR receptors, and we figure that because our fusions were done on the C-terminal, that prevented an appropriate binding of our dominant negative MyD88 to the TLR receptor, and that gave us some problems. But still, if we conducted our future experiments without the C-terminal addition, our constructs would still have to work now. Did they? Yes, they did. The blue columns here represent the control. You can see that with increasing time of stimulation, there is an increase in the level of induction of the NF-kappa B responsive promoters. The red columns represent the cells that were transfected with the dominant negative MyD88. And yes, a decrease in the level of stimulation is evident. So we can conclude that our feedback device really works. We have transferred the BrioBricks principle into mammalian cells using transient transfection and have successfully implemented the feedback device that restricts the cellular activation by bacteria. Our constructed device mimics the natural mechanism of tolerance, only that it is activated faster, not in days, but in few hours. And a simplified model of TLR signaling qualitatively captures the main feature of the signaling kinetics. Still, there is some work to be done. We could regulate the lifetime of the inhibitor based on different rates of degradation using the PASTE tag. The PASTE tag, unfortunately, wasn't tested in our experiments because it was also added on the C-terminal, which proved to be not so successful. And still, we can construct BrioBricks vectors for stable transfection using additional resistance for cell culture lines. Well, for the end, let me say hvala lepa for your attention and conclude that we are very honored that we were able to give this presentation for you all. So thank you very much.
Dobar dan.